It is not polished stock of the accomplished results. It's more in progress stock of an interesting problem that some of the attendees may get inspired and contribute later, or may see it as a part of the coursework for education, or maybe it will convert into something. So this talk probably could be presented again in a couple of months in a better shape and with better presenter, whoever will continue the subject. So what is the subject? And by now the best expert in the at the NDSU on the subject is today's attendee Stephen. So in some sort I borrowed inspiration from him and will tell about it a little bit more, and he will maybe continue later on. So two-dimensional magnetic materials. Why it is challenging, and what are the benefits for the community, society, and for the science? So general magnetic materials are good for information storage, like in hard drives. And in the novel era of quantum computers, there is a constant search for materials that can hold individual spins with coherence and interference effect. So general interest to spin materials is present. So it is the use of these materials to the society. What is the challenge? If magnetic centers, which are transition metal ions, are arranged in a plane, they have less neighbors than in three-dimensional magnets, and they have more neighbors in one-dimensional string. And these circumstances create frustration. Not only frustration in researchers who deal with this area, but also in individual magnetic moments on the atoms, individual spins. So if the number of neighbors for a given ion is not large enough, then the central ion affect neighbors approximately in the same measure as neighbors affect the ion. And several opposite configurations have equal energy. So there is degeneracy of energy in drastically divergent orientation of spins and magnetic moment. And since the system does not know which configuration to take, it feels frustrated. And what it means for researchers that a lot of well-developed and tools that are efficient in all other situations are failing. So one of the workhorses in the research among attendees of the class, sorry, not the class, attendees of the meeting, is so-called density functional theory, which is not the most precise, but one of the most numerically efficient methods. And it is based on the single determinant of approximation, where one neglects coexistence of several configurations of multiple spins. The system, when these transition metal ions with spins are enforced to be in plane, goes beyond this picture. So predominantly final observables, final results cannot be obtained with DFT. And it is one of the reasons, because the slide that I'm going to show will have no DFT, no ab initio calculations on one hand. So it will be only model calculations. And there will be no derivations and equations, because if one goes steps on this path, it will be substantially challenging. So it is the easiest way to say something. Well, I have a lot of other things to tell by words, but just if you are bored to listen to me, I'll start sharing some pictures, even if they are ugly. Okay, so the material I'm going to talk about is ruthenium chloride, but the consideration goes beyond this material. So it is any material with three neighbors in plane that creates instability. So this ruthenium 3 plus and chlorine minus ions are arranged in such way so that each ruthenium is surrounded by 6 chlorines. But 3 chlorines are, so to say, attributed to host ruthenium, and 3 others are from another neighbor. So it's like ruthenium chloride 3, ruthenium chloride 3 makes a 2-dimensional chain. And in this arrangement, each ruthenium is in octahedral environment, and then the spin, the d level splitting looks in the typical octahedral way with T to G group of levels is occupied with 5 electrons. So the spin is unpaired. So this each ruthenium ion has 1 unpaired spin. And in this ugly diagram in the center, I am not showing any chlorine ions, just because it will be too busy, too much. So it shows only ruthenium centers, which are surrounded by chlorines. And ruthenium centers do form the honeycomb structure in the same way as carbons in graphene or in nanotube or in buckyball. Well, not buckyball doesn't work. Graphite are setting up. And for such hexagonal honeycomb lattices, the minimal element of the pattern that is being repeated and that is would allow to reconstruct the whole structure will be this little diamond. And this diamond includes 3 basic units. So there are these circles correspond to ruthenium ions, and one can see that it neighbors 1 ion inside the cell, and then 2 ions outside of the simulation cell. So there are these green neighbors and purple neighbors. And then if one goes forward and replicates this unit cell, then probably one can identify this B honeycomb lattice. The interesting feature that in order to make this minimal cell, one needs to avoid 90 degrees coordinates and do this tilted system of coordinates with basis vectors A and B. So what is the goal? What is the observable, and what is the instrument? So the system of interacting spins is hard to do with ab initio electronic structure, is too much intellectual effort to derive equations, and the only way is to do model simulation. The attempt to make theory of everything is not constructive, so it would be healthy to select maybe 1 or 2 observables that can be compared to experiment. And for this system, just I do not want to miss, let me show you something. You may have seen there were wild turkeys outside from the window. So the observables that one can track is magnetization of the system, which means total number of spins up minus total number of spins down. The total energy, which is average energy by making average over ensemble of microstates, and heat capacity. how this model responds to thermal equilibrium and at which temperature it will accept more or less energy. So the simulation is done in several steps. So there is a little code that is set up to model the final observable, the heat capacity. So if one looks, if you start from the end, it will be easier to get through, and maybe some details can be skipped. So if there is a way to find average energy as function of temperature, then one can go along this line, practice derivative, and find heat capacity. And this is something that one can measure experimentally, relatively cheap, inexpensive, and this is information that one can find online in previous publications. So the way to get this average energy can be sketched in a quite quick and simple way. So one way is to scan through all possible configurations, like make a simulation cell of several spins and practice a cycle, take all spins up, then one spin down, then two spins down, take all configurations, and for each configuration find the energy of microstate, and then perform populate each microstate based on the Boltzmann factor, and then make an average. So this would work if number of the sites, number of these ruthenium ions is small enough. But let me maybe make an empty slide and do a freestyle comment. So if there are one side where spin can be up and can be or can be down, then there are only two states, right? If there are two sides, then total number of configurations will be up, up, down, down, up, down, and down, up. So total number is 4. And if one goes further, then the total number of states will be 2, because spin has 2 states, to the power of number of sites. So if it is bigger than, let's say, 30, it will be not numerically efficient to scan over all possible configurations. And in such situations, one practices so-called Monte Carlo simulation, when one selects random configurations out of all possible configurations, process them as needed by finding energy of microstate multiplied by Boltzmann factor depending on the temperature, and then adding it to the average energy. So this is a reasonable approach, and there is one technical aspect in implementing it. So to do so, it is really desired to make sure that among these random configurations, one takes into account the ground state, if it does exist, if it is available. And it is just a little observation from first attempt of simulating. If ground state is missed from partition function, from this expectation value of energy, then the results as function of temperature accumulate a substantial numerical error, because the lowest energy microstate gives major contribution to partition function. So if it is removed, then results will be not trustable. And it is reasonable to include for sure the ground state if it is available, and then for all other states practice this Monte Carlo approach, which Monte Carlo comes from the name of the gambling site in Europe, where one throws dice and plays gambling. So in fact, one first does a unit of finding ground state by optimization in this model space, and then scan through random microstates and find contribution to partition function, contribution from each individual microstate to average energy, and also find contribution to magnetization. And the energy of each microstate is computed by so-called Ising Hamiltonian, which means one accounts contributions from all neighboring sites, neighboring spins, and their contributions come either with positive or negative sign depending on the spin-spin coupling constant. So this coupling constant is something that determines the nature of the model, and it is where ab initio calculations would still be applicable here. So it means what's the difference of ferromagnetic and antiferromagnetic configurations. And also one needs to include magnetic field and add the interaction of all spins, Zeeman splitting of all spins with magnetic field as a portion to the energy. Why it is needed? Would it be simpler to remove interaction with magnetic field and have shorter expression for the energy? Without magnetic field, much larger number of microstates will be degenerate and will create a mess and numerical instability. So magnetic field, even if we do not have magnetism in our actual experiment, is has some healing nature for the calculation. So it heals from numerical instability. So it does provide, it lifts some degeneracy. And later on, if one continues, one can make magnetic field of the lower intensity and then see what happens. So what is to expect? And I will show a couple of slides with example of the simulations, and then we'll discuss, and probably either it will be so boring that no one will ask questions, or there will be so many errors that everyone will ask questions, and discussion will be longer than the presentation itself. So the actual ruthenium chloride material is known to be antiferromagnetic and have positive value of this spin-spin coupling. But in order to verify that model works well, one can look on other types of materials. Ferromagnetics, when spin-spin coupling is negative, when it mandates all spins to look into the same direction as more energetically favorable, and zero when spins do not interact with each other. So the actual result of interest is only the last situation, and first two are just tribute to curiosity and a way to justify the model. So for each model, and I give a disclaimer, it is not polished results, and some figures are ugly, some are missing, so it is only a sketch of a work rather than set of results. But as a plan for each model, for each set of couplings, one can identify, one can look over the microstates by analyzing them in form of density of states, same way as many of us analyze ab initio data. So, but it is different density of microstates. Then scan temperature, record energy, and find the heat capacity. Later on, one also can scan magnetic field. And this pattern of density of states, temperature, and heat capacity will be repeated for each set of couplings. So for the situation when coupling is zero, it will correspond to paramagnetic, where direction of spins follows direction of external field. The spin-spin interaction is excluded, and basically it will be collection of independent, so many independent spins, and it is one of the few models in statistical mechanics and quantum mechanics that can be solved by pen and paper. So it's just one line solution, and I'll show it as a reference point. For ferromagnetic, one expects that if temperature is lower than some critical Curie temperature, all spins will be in ground state oriented collinearly, and as temperature exceeds some critical limit, they will start being random and come to paramagnetic state, and magnetization will be lower, and it will accept less energy. And for antiferromagnetic, there is a chance that it will be numerical instability, and there is a chance to experience true degeneracy of the ground state. So it may just fail to compute, or there will be something on one hand interesting, and on another dangerous behavior at lower temperature. And if the audience was attending talks of Stephen on this subject, he was explaining what is spin liquid. I'll try to avoid this the discussion. So in the next couple of slides, I'll just show examples of the microstates, which are the building blocks for this simulation. So, and I apologize, it's not polished, it's only a sketch of a work. So, and we all get good custom to watch high quality figures of atomistic models. This one is not atomistic model, it's just a visualization of model Hamiltonian. So the model here includes 4x4 unit cells of this little diamond with two ruthenium atoms. So it will be 16 by 2, 32 sites. The sites, which are symbolized by these green circles, are placed in the vertices of this honeycomb, and at each side we have a spin that can be oriented up or down, and it is symbolized by these little sticks which are up and red if spin is up, and down and blue if it is down. And the magnetization is number of spins up minus number of spins down multiplied by 1/2, if we believe that each spin has at each point there is one spin of the value 1/2. And here are example. Here there are 16 unpaired spins. There are more red than blues. Here 8 more up than down. Here are 6 unpaired. Here is 1 unpaired, so they are approximately equal in going up and down. And such configurations form a building block. So at each temperature, each value of magnetic field, one needs to take 2 to the power to the big power, too many of such configuration, and find the contributions. But instead, one selects them randomly, and in the results that will be shown, there is 20,000 microstates for each value of temperature. So first, couple of results for ferromagnetic case. And I know that couple of attendees of the audience have seen next few slides for paramagnetic, but what will be new today is paramagnetic and antiparamagnetic. So first, density of state. If we have so many microstates, we can save their energies as a table into file and process them by plotting a peak or Gaussian function each time we see a state. And if there are more than one, then it will be taller. So if we truly follow this procedure in the same way as we do to analyze orbital energies, the amount, the height of these peaks will be different by orders of magnitude, because some of the states, especially when spins are paired, are highly degenerate. So it's like several of orders of magnitude different, and most important, ground state peak is not visible on such representation. But if one takes log scale, then one put more attention on this strongest and weakest peaks, so one see more information in the same range. And there is a pattern of individual state, and then the degeneracy grows and falls. So one can interpret total number of peaks is 32 plus 1, and one can interpret each peak as a certain number of unpaired spins, like minus 16, plus 16, and stuff in the middle. And they are shifted from the center because magnetic field is non-zero. Okay, so what happens if one scans the temperature and computes partition function, expectation value of energy, and expectation value of magnetization? So with increase of temperature, more and more of these microstates are getting populated by Boltzmann factor. And since lowest state has certainly the maximum magnetization at lowest temperature, only this magnetization contributes to the total magnetization. Since the lowest state has certain energy, -1 in some units, at lowest temperatures, only the lowest state will contribute to average energy of the system. But as we increase the temperature, more and more microstates will contribute, and magnetization will become smaller and energy will become bigger. So here is the energy. And until the temperature, and x-axis is temperature times Boltzmann constant. So until the temperature goes sufficiently high to overcome the subgap between ground state and first and next state, the average energy is constant as function of temperature. And as one goes further, the average energy becomes higher and higher because more states contribute to the expectation value. So by practicing derivative of this energy, one can extract heat capacity, which means ability of system to absorb external heat. And when we are about in the middle of this point, the slope is the steepest, and the derivative is the highest. As we go heating further up, it will absorb less heat. So in this specific example, these lines are quite smooth, but in some other examples and sets of parameters and different dimensionalities, this behavior can be more sharp, even looking like a step function. And then some people consider it as phase transition. for example, between magnetic, ferromagnetic, and paramagnetic states. So if we look on the magnetization, and here it is just dimensionless in the number of unpaired spins. So for ground state, it stays ferromagnetic until one heats it up high enough, and then also it starts growing and approaching zero. So at infinite temperature, amount of spin up and spin down will be equal, and it will be vanishing magnetism. So next attempt is to try to set spin-spin interaction zero. Literally putting zero by some reason. Oh, someone is typing a question. So there is a question in the chat line. So I will answer it and then go forward. Levi is Dr. Weistrom from National Lab is asking about geometry optimization. No, there is no geometry optimization at all, and we are not considering. We are not in this calculation. We are not considering positions of ions as function of a coordinate. So they are nailed down. This is completely out of question. Otherwise, it will be undoable. The analog of geometry, of not geometry, but analog of optimization, is hidden in this step. So finding the microstate with minimal energy, which means one can find such configuration of spins that gives minimal energy. And it is not necessarily when all are down or all are up. It can be different. Okay, so I did try to literally put j equals 0, and the code exploded, started to give garbage. So it doesn't like it. But if one uses maybe slightly negative, like 10 to the minus 6, then it works okay. And I think we can assume it as good as paramagnetic. So the density of state becomes a little bit more symmetric, but still the ground state is offset from the next state, because magnetic field is non-zero, so it is of the so it's some non-zero value that provides splitting of all states. So if one would remove magnetic field, then all states will become degenerate. And there are two reasons for degeneracy. One is spin-spin interaction, and another is Zeeman splitting due to magnetic field. And here, spin-spin interaction is put as close to 0 as possible, but magnetic field is yet kept non-zero. Another question, Sean is asking, how do you look to differentiate local versus global minimums for magnetic states? Is scale fixed? This is a very practical question. Thank you, Sean. So I will go back to this flowchart diagram. So what we do here is set up random orientation of spins, flip one, check if the flip of one spin increases or decreases energy. If it decreases, we accept this flip and then go again. And repeat it several times until the system finds the minimum. But there is a way that this minimization will drive us to the local minimum, and it will be trapped there. So there will be no path to go away from local minimum by flip of one spin. This is possible. I'm not going to fight it. I am just going to accept it and make a plan how to interpret it. So on one hand, we did very large number of attempts. So if the total number of configurations 32 and approximately 32, not configuration, spins 32, we should arrive to a ground state. I put it 32 times 1,000. So for sure, it should come as close to ground state as possible. But still, we can be trapped in the local minimum. But when we perform this cycle and try a slightly different temperature, since everything is based on random numbers, the system will bring us to another local minimum. Like if there is a global and several local minima. So if we randomly go, we can go into either one or another one. And if you have large enough number of numerical experiments, then at least in one we will come to global minima, or if they all are equal, we will have a representative distribution of local minima. Sean, does it answer your question? You can just show yes, no. Or say or type no if it is not sufficient. Mute means everything is okay.
I'm just trying to think through a good response. Sorry, it might take a while.
Okay, and I'll go forward and feel free to interrupt anytime. Okay, 0 paramagnetic. So the results for energy. Yeah, by some reason energy is not included, but derivative of energy is shown, and it looks more ugly and more numerical instability. And compared to ferromagnetic case, it is shifted to lower temperature, and it looks much sharper on one hand. On another hand, just to numerically process these results, I was trying to practice some homemade spline that makes this curve a little bit more continuous. And it seems to show the peak at the same point, about the same width, but remove this numerical instability. This result of the energy, which is by my error is not shown, energy, magnetization, and heat capacity is one of the possible problems to solve by pen and paper in one line. And here is the solution. So if we need to find energy of system that can be in configuration of spin up and spin down in magnetic field, we are taking energy of spin along magnetic field, which will be spin times magnetic field and or magneton with negative sign times probability to find such configurations, the weight, the Boltzmann factor, plus energy of the less favorable energetic place where it comes with sign plus, and this x is just energy divided by Boltzmann factor. So we have energy times Boltzmann factor, energy times Boltzmann factor, and in the denominator we put partition function, which is summation of these Boltzmann factors. Since there are only two configurations, there are only two Boltzmann factors, and they add together. So this is partition function, and together this is expectation value of energy. And then by definitions of hyperbolic sine and cosine, one can treat this as hyperbolic tangential function, which looks as a step function, and derivative will be quite close to this function. So comparing to reference point, I'm not showing two lines on the same figure, but there is a plan to do it, and they are expected to coincide very closely. Okay, so this was the plan to justify the methodology, and here if the number of spins is more than 2 but they do not interact, one just puts places total number of spins as a factor here and there. So paramagnetic solution, the energy as function of temperature. And the actual result here is magnetization. It also shows magnetically oriented, and then converts to paramagnetic case. If I flip this line, if I take absolute value and look how it decays with temperature, it will be something like 1 divided by temperature, or 1 divided by some critical value minus temperature, which can be found in Wikipedia as something like Curie law or Curie-Weiss law for magnetization of paramagnetics. So there is another point of comparison through Wikipedia. So if while listening you find it and catch me lying, please do. It will be only help for progress of this project. And I have very few slides left, but they are the only relatively novel scientific value. So anti-ferromagnetic case when the coupling is positive. So the density of states seems flipped. So if I'm going to go about 10 slides back for ferromagnetic case, we had all oriented parallel at the minimal energy, and then it goes up and drops. Now, if we go to antiferromagnetic, it looks like things are being flipped in respect to 0. So in antiferromagnetic case, when all spins are collinear, this will give maximal energy. So it will be most energetically inaccessible configuration. But still, there is a non-zero magnetic field that provides some Zeeman splitting. Therefore, we still have not as big degeneracy at the lowest state. So it is degenerate, but not as substantial. One may expect that if magnetic field goes to 0, then the density of states will start with maximal value right at the at 0 temperature, and it will be mostly numerically unstable and challenging. So the ground state will be substantially degenerate and will create a big headache on one hand and some interesting solutions on another one. So if one practices an attempt to find average energy, due to this degeneracy and multiple possible local minima that Sean was asking about, the numerical values have substantial, they differ from each other, the error bar is big, and even if one performs this spline procedure, it also doesn't go like a smooth line, it also has some noise. And it has this strange behavior quite close to zero temperature, and then it starts increasing. Also, there is a interesting observation that I do not have enough experience and knowledge about this class of system, but I don't know how standard it is, but it looks like slope of the energy over temperature is negative at initial steps. This is not expected. If it is correct, it is highly likely it is just an epic failure, or very unlikely it is some discovery. The decrease of the temperature with decrease of the energy with increase of the temperature is typically corresponds to negative heat capacity, and it corresponds to non-equilibrium systems. For example, the laser in generation regime, where there is a set of excited atoms or excited molecules. If one creates a solid that brings it from this metastable state, then there is a chain reaction in avalanche way, and it drops the energy. And in some sense, external perturbation, increase of temperature, may induce the drop of overall energy of system. So such exotic systems can be imagined, but not in the system small simple arrangement like here. So likely this is just numerical instability, but one may check again and again. And then it goes up quite rapidly. So approaching it goes quicker than 1 over temperature. It goes quite dramatic. So the derivative, as expected in this regime, is also not a very well defined. It is derivative of a spline function, and it still has this numerical error, which was not there when we used paramagnetic and paramagnetic. And it approaches zero at large temperatures, like close to zero. And here it is something numerically unstable, and likely it will be just a maximum, but maybe that I want to be very cautious and just read more about it. It shows several points with negative heat capacity, which is likely an error. And the magnetization, so at higher temperatures, it should behave, and it behaves like a paramagnetic, but at as approaching to 0 Kelvin, it shows instability and very broad dispersion of possible values of magnetization, which can be a nature of the model that one cannot do anything. Second, one can try to increase amount of microstates per one average per one ensemble, so from 20,000 to like a million, which will slow down calculation substantially. Or maybe it should be a collective state which cannot be described on this quasi-classical Ising model, and one needs to use true quantum state with diagonalizing Hamiltonian and allowing superpositional states. Okay, so we did consider ferromagnetic, paramagnetic, antiferromagnetic. It was on the honeycomb lattice for ruthenium chloride. And with this, I would like to stop slide because there are no more slides. Thank you for your kind attention, and any questions are welcome. Thank you, Levi, for seeing symbol of about. So there is a question from Sean. Does the frozen core approximation significantly impact quality of results for these models? Would you please define what is frozen core? Just to make sure that we are speaking about the same thing. Yes, it is. I do not have like mathematical proof, but it is a standard practice. So for any processes related to chemical reaction or physics of conductivity or magnetism, where typical energies of excitations and energy of sets are of the order of 1 electron volt, the core electrons can be neglected without any consequences. So it is not a proof, but it is a standard practice. And as long as spin-spin interaction is lower than 1 electron volt, and it is typically lower than room temperature. Will you return to slide? Yes.
Thank you, Professor. So you have average energy as opposed to like specific heat, just to make sure that we're understanding this graph in the same way.
Yes, it is average energy.
I asked because one of the paper that inspired this idea to begin with had a figure that graphed specific heat versus temperature, and they actually found a very large spike in data experimentally at around like about 10 Kelvin.
Mm-hmm.
I apologize if I missed that. I was, if you explained that already, I was just making sure that I was understanding that graph correctly.
Yep. So they found spike for heat capacity?
Yes.
Okay. Yeah, then it is the by 26.
Okay.
So
yes. All right. Thank you. That answers my request.
So any questions, criticism, constructive suggestions, or even non-constructive suggestions? So if I have a question from, what is the origin of numerical instability? I think it relates very much with the question of Sean. Not that I'm telling that Sean is responsible for this numerical instability, but he caught he asked the correct question. This system, this kind of systems, do often have the degenerate ground state, which means there are multiple local minima, if these words are applicable. It's analogous to multiple local minima. And different local minima provide different contributions, are responsible for different contributions to expectation values of this and that variable, on one hand. On another hand, if the amount of microstates explicitly considered in this random ensemble is not sufficient, then some of the local minima highly likely can be missed. And if the local minima, or at least one local minimum is missed, it withdraws substantial portion from this expectation value, from average observable such as energy. So the silly, straightforward way to minimize this numerical instability is just to use larger and larger number of the microstates. And for this 32 ions is not as huge. So hypothetically, one can scan over all microstates and minimize. If this is not helping, another possible way could be to consider it as truly quantized system with finding eigenstates instead of randomly sampling this basis microstates. Did it answer the question? Yes. Okay, thank you. Next question, Sean. Could a dynamic tree search be used to assist in reducing number of trials for finding minimums, like the article linked? Possibly, I don't know. This Monte Carlo simulation is the simplest way to address and approach such kind of challenges. I do not exclude that there is a smarter ways to sample over these microstates and even identify some trends, and maybe we can check with collaborators who practice machine learning and cheminformatics if there are some ways to identify minima in such class of systems, because with seemingly large number of configurations and challenges, it is still a model system that is possible to treat under laptop with short time. So it is much simpler than typical consideration of real molecules. So one can practice several methods, including this dynamic tree. Yeah, thank you for finding this this option. Sure. Thank you, Steven, for giving credit to Sean. So let's check if there are more questions verbally or in the text format. Let me check with Professor Asulev if problems of addressing multiple, or finding browsing through multiple local minima is something standard in the machine learning community, or it is a little bit more to physics.
It's not really standard. Yeah, thank you for addressing it. It's not really standard, but that's actually what is, let's say, in demand lately, and several groups working on this kind of stuff. Yeah, it's possible.
Okay.
Yeah.